discuss how to combine or how to apply LLMs, if possible, to DeFi security. And before we do so, I think I'm quite grateful for the previous speaker because he kind of shared that there's roughly $1 billion US dollars lost per year in DeFi attacks or so-called hacks. There's also roughly $500 million US dollars per year that's extracted from arbitrage, liquidations, and sandwiches. So I unfortunately don't have any formal definition of what an attack really is. So please don't question me too much of how I define a DeFi attack. But roughly speaking, we can think about these kinds of orders of magnitude that are being lost or earned, depending on which side you are. And these numbers naturally depend on the market fluctuations, on the market prices, and so on. All right, so this is roughly the order of magnitude of the markets. And if you want to look into more details of how these attacks are being distributed among several cases, we've written an SOK paper, so like a systemization of knowledge paper that tries to classify attacks. So we've looked at attacks over a 4-year time frame. We've looked at roughly 200 attacks and categorize them in a big table and try to make sense of how repeatable attacks are as well. And they do seem quite repeatable in many instances. Now, a paper obviously is just a snapshot in time in this case. So I would really recommend you to check out, for example, defilama.com/hacks if you want to get a more updated list of DeFi attacks. So the community is beautifully working together on documenting in detail every single hack that's happening out there. And there are also other websites, for example, Blocksec has an incident website where they try to collect proof of concepts. There's a fantastic GitHub repository called DeFi Hack Labs. So these are all great resources if you want to understand what DeFi attacks are, how they work, how can you reproduce them, etc. So the one of the most important elements when executing an attack is to follow the supply chain. So to follow kind of the way of how they get executed, right? What's the process from when the adversary starts to sign the transaction and then sends it out? So where does the adversary actually send out a transaction? So for example, an attacker can submit a transaction to the peer-to-peer network. If a transaction is sent there, then you would expect, and that's typically the case, that everyone that's subscribed to a particular peer-to-peer network can also read this data, right? In this particular case, it would be transaction A. Now, if I'm an arbitrageur or I'm a front runner and I would like to front run or arbitrage this transaction TXA, then I have a set of options of what I can do with this particular transaction A, right? So, for example, if I want to perform an arbitrage after TXA, right? So attacks are typically large volume transactions. You can think of order of at least 100K US dollar per transaction in terms of volume. Then these naturally cause arbitrage opportunities on all the DeFi pools. So I may want to place an arbitrage transaction right after this particular attack transaction. So that's called backrunning, right? Because it's after the TXA transaction in this case. So I can do two things. Either I go through the peer-to-peer network, right? So I can just send my arbitrage transaction out. Since it comes afterwards, I pay also a little bit less gas than TXA, and I can expect that the next validator, or more specifically block builder, is supposed to mine it after TXA in the sequence of executions. And another alternative would be to send it over over block builders such as Flashbots, Beaverbuild, and so on, where I place a bundle. So I submit these two transactions together, and I specify I want them to be executed in this very sequence, right? TXA and then TXARP, right? Not the other way around, in this very order. Now, another alternative here, what I could do if I'm a front runner, I could place a transaction TXA prime in front of the, I could basically front run the attack by, for example, copying it, right? I can modify it, and then I can also do an arbitrage behind, right? So there are different ways of kind of handling with this data, right? So the supply chain of how transactions eventually make it in the chain is quite crucial in executing attacks. And why am I speaking so much about executing attacks? Well, we can only defend against attacks if we actually know how they really work and how we can execute them, right? So that's the whole point. So let me go through one specific example of an attack. This is the elastic swap attack that was carried out in December 2022. It's a particularly interesting case because it happened, like a similar thing happened on two chains. So there was one attack that was executed on the Avalanche blockchain, as you can see here on the top right with the red logo. And here time, so this time axis indicates real time. So it's actually not the blockchain time, right? Blockchain time would be the audit transactions once they're mined. Here, what I'm trying to convey is really just the real time. At what point in time did we observe certain transactions, right? This is just to help you a bit understand this, the evidence I provide here. So now let's do a bit of forensic. So can we understand what really happened? I mean, I have already some labels that try to give away some of the logic, but let's go step by step. So here we have the Avalanche blockchain, then we have the Ethereum blockchain, and so we have one transaction on Avalanche, 3 on Ethereum. All right. What does this green and this red icon here mean? Well, this green icon here depicts a transaction that was successfully executed, successful in according to the EVM execution environment, right? So you can have a reverted transaction if certain conditions in your transaction or smart contract were not met, then you can revert a transaction. So that would be identified by this red cross, right? So this is not successfully executed, attempt to revert the state changes that the transaction did. Okay, so we have 2 successful executed transactions and we have 2 failed transactions. Now, if you look at the Avalanche blockchain, there's only one transaction, right? So it's TX0. So in somebody, we call it here the attacker in quotes, called the go function of some contract. Right? You can rather easily identify what kind of functions a transaction calls. So in this particular case, is the go function. Then, like a few minutes after, we've observed with our spy node. So we have a spy node on the peer-to-peer network. We get accurate timing information of when we see transactions. Then we saw another transaction that also calls the go function, and it propagated on the network, right? However, later, right, this transaction was actually not mined successfully. It reverted. And there are 2 other transactions that came about, so TX2 and TX3. So here we can see some funny things. So first, only one of them makes it, right? So this is the one that executes successfully. And this one calls the function not yoink, while the other calls the function yoink. If you look at the supply chain of how this transaction was mined, you would observe that the last one here was sent over the peer-to-peer network, while the TX2 was sent over a PBS system. So it was sent to a builder, who then built the block, sent it to a relayer, and the relayer forwarded the block to a validator, which eventually mined this block. So what else can we see? Well, it seems like here the time difference, right, between TX1 and TX3, the observed time between these 2 transactions is only 250 milliseconds. So this suggests that the way that transaction 3 was created, it must be some automated mechanism, right? Because this can't be done in manual time. At least I can't be that fast. So there must be some manual process, I suppose, right? So and eventually we only have one transaction here that was successfully executed, right? So I'm sure many of you already understand what's the implication here, but it appears, right, that TX2 was a front runner, right? It kind of observed this transaction 1 that propagated on the peer-to-peer network, and TX2 and TX3 are front-running transactions that attempt to front-run the transaction 1. On Avalanche, there was no front runner, right? Nobody was front running anything. The attacker quietly and in a very relaxed way seems to have executed an attack, right? Whereas on the Ethereum blockchain, right, where there was this Yoink fella, and he somehow managed to front run apparently this transaction one. We can see this because transaction one is the transaction we observed first, but it did not execute successfully. Right? Okay, so what can we learn from Yoink? Well, Yoink seems to be some kind of a white hat hacker, which has bilingual capabilities. So he's speaking both on the peer-to-peer layer and and through relayers. He can mimic and front run transactions in less than 250 milliseconds, and he's really good at bribing too. So the overall attack yielded over 500 ether, of which 15% were used to bribe the relayers, and 10% was given to as a bounty, or was taken as a bounty by Yoink, right? So these numbers are kind of like market standard rates, which the community somehow agrees to are ethical. I don't know why, but this seems to be the case. Okay, so this gives you roughly like a very concrete view of how an attack can be executed and what are the different supply chains that happen, right? So how can we defend against these kinds of attacks? Well, audit, like for example, smart contract auditing is a really helpful way, right, to secure smart contracts, but it cannot be the only answer, right? We really seem to have the need of a defense in depth approach where we do certain things before the smart contract deployment, so pre-deployment, so an audit, so we can define transfer limits, we include pause mechanisms in a smart contract. But post-deployment, there are a lot of things we can do, right? We can build intrusion detection and prevention systems. We can proactively search for vulnerabilities on the given blockchain state. We can look for similar attacks. We have found that roughly out of the 200 attacks that we looked at, I believe we have found at least 30% of these attacker contracts are 80% similar to each other, right? So you can create embeddings of smart contracts, and then you can look at their similarity. You can compare, for example, the attacker contracts. Attacker contracts and vulnerable contracts both are actually similar. So we can really learn from past attacks. And even if you are attacked, right, even if a protocol was exploited, you can still try to extract whatever's left. So we have seen several instances where attackers are in fact not using optimal parameters and therefore not extracting everything that's left on the table. So you can still take the rest there, right? So security is really always a defense and depth game, and the same applies to smart contracts. That's really the high level message I would like to convey here. And with this in mind, I would like to propose or discuss really an intrusion detection method. It is we call it BlockGPT. It is, if you want, you can think of it. It's like a simple GPT-2 model that's specialized for blockchain transactions. It is really a prototype. I don't think this is production ready at all, but it's a glimpse into what could work, what could be an additional intrusion detection signal. So when I speak about GPTs, I think it's really crucial to make a different distinction between what is a ChatGPT kind of model and what is a GPT base model, right? So if you look at a GPT training pipeline, so it starts here on the left. So the first step is the so-called pre-training phase. So here is where you have a big data set, for example, the raw internet, and then you learn you learn to predict the next token, right? A token is not a cryptocurrency token in this context. It's really just a set of a few characters in the natural language processing context. And this gives you a base model. So today I'm really only speaking about this base model. I'm not speaking about anything afterwards, right? So there's no supervised fine-tuning, there's no reward modeling, there's no RHLF to create a ChatGPT model in this talk, right? I'm really just speaking about the very first like step to keep it simple and to give you just a context. But I took this picture actually from Andrew Karpathy. He explained this very well, and it was really helpful to to understand the different nuances between what different models actually exist and what are the stages in the training pipeline. So what are the challenges when we want to apply now, for example, LLMs or even just conventional ML-based methods to intrusion detection of DeFi attacks? Well, we need some kind of a binary classifier that distinguishes between what is benign and what is malicious. And DeFi has only a limited set of attacks available. So, for example, DeFi Hack Labs, I believe, has about 400 attacks that are currently available on mostly Ethereum and Binance Smart Chain. And that's just not enough data, right, to train big neural networks. So, yeah, the attack data points per year are really small. So we can't just apply traditional kind of classification as far as I'm aware, but maybe you find a way. So what we did, we took a data set of unlabeled transactions, so roughly 68 million transactions from 150,000 days of victim dApps that were eventually hacked, right? And these victim dApps resulted in roughly 124 DeFi attacks. And this is our labeled data set. So we have an unlabeled data set, right? So, and a labeled data set, this is for evaluation afterwards. It could be that in some cases there are multiple attack transactions per dApp, right? But this is roughly the data set we're talking about. Now, 68 million transactions, so most of them obviously are benign, right? These are just regular transactions on how people interact with the DeFi protocols. That already starts to be a more reasonable data set if you want to train a machine learning model. So what we did in essence is we took here a set of transactions of a DeFi application, right? So TX1, TX2, TX3, just regular transactions. And we trained a GPT model, right, to estimate the likelihood that a certain transaction exists. When I say that, I'm actually glancing over a lot of technical details. So if I want to be a little bit more precise, I would tell you for each transaction, we plot the trace, so the execution trace at the opcode level, right, of each transaction, and that's a sequence, right? You can think of it as a stream of characters. It's like a text, really. And based on that stream of characters, we try to learn how likely is the next opcode in a transaction execution, right? So it's very similar to a human or to natural language text, where you predict the next token. So the fox is brown, right? You know which next word to predict or which next token to predict, right? And the same applies to really transactions. You can also try to predict what's the next likely opcode when you execute a transaction. So this allows us to estimate the likelihood of a given trace. And then what we can do is, given a new transaction, right? So once we train the model, we get a new transaction as input, and we can try to rank it, right? We can try to have some manual alarm threshold, and this is actually a parameter that will define your rates, your false positive rate in this intrusion detection system. So based on your appetite for false positives, you can be more or less lenient on the alarm threshold parameter. And then it will give you a rank here, relative rank among these 4 transactions in this example, right? And if it hits above your threshold, then you could say, well, this is an abnormality. I may want to, for example, pause my smart contract, or I may want to delay some transaction, first investigate. Yeah. So these are the possibilities that you could have afterwards. So if you want to go a little bit more on the technical side, you can think of the pipeline as follows. So we have a prepare step, right, where we have a blockchain archive node. We get the opcode, we get the state trace, we get the function trace, we get the log trace. We combine all of these into a process trace. Then we have an embedding layer, and then we have a transformer encoder, right? So this is roughly the architecture on a bit more technical side. So what are the advantages of such an approach? Well, there's no engineered rule, right? This is purely data-driven. So if I go back to the slides here, it's purely data-driven. Everything is trained on this 68 million transactions, right? We learn how do transactions look like. That's really what the model learns, right? It learns what the transaction trace is. And there's no engineered rules. There are no heuristics, right? And what we found is that it can potentially detect new attacks that are not covered by any known rules, right? So, for example, you could have a heuristic if the transaction is transmitting at least whatever $1 million US, then it's malicious, right? So that's a very naive rule, I would say, right? But sometimes we found that BlockGPT detects non-profitable sanity check attack transactions. So sometimes the attackers, they execute a transaction that is already an exploit, but they execute it in a way that it doesn't transfer a significant amount of funds, maybe just a few bucks to test. It's a sanity check whether the attack works, and then they can execute it properly. Don't ask me why people or attackers would execute sanity checks on the public network. I have no idea why they would do that, but it did happen. So it's just interesting that BlockGPT can find the structure of some of these attack transactions as being abnormal, not only the amounts that are being transferred. So the results that we have are the following. So we have, out of a set of 124 attacks, right? BlockGPT ranks 20 as the most abnormal, 20 as the second most abnormal, and 7 as the third most abnormal attacks. So you can see this is in total 47 out of 124 attacks are ranked as the top third most abnormal attacks, right? So I'm not too confident to judge now on how to define a false positive rate or like a success rate in general. It really depends on your setup. For each DeFi application, you would need to set your false positive rate appetite, right? So I think the conclusion is there are definitely false positives, right? This is by design, actually, because you have this threshold that defines your appetite for false positives. But the system is surprisingly capable of detecting a non-negligible amount. Here in this case, let's say 47 out of 124 attacks as the 3 most abnormal transactions, right? So,
Arthur, a small reminder, we're running a bit short in time.
Okay, yeah, I'm done actually. Okay, thank you. So, and the last thing I wanted to share is the throughput that we tested on one GPU is 2,000 transactions per second. So this can really scale. This was just one GPU. It's an unoptimized, I would say research prototype, so to speak. And thank you. Yeah, any questions?
Yeah, amazing talk.
Have you done any amazing talk, by the way? Yes. Have you done any kind of analysis on how well the model generalizes on attacks? Because it might be that it detects certain classes of attacks now, but yeah, can you say anything about new types of attacks, perhaps?
Yeah, that's a great question. So the 124 attacks that we looked at were attacks over a 4-year time frame, right? So between 2018 and 2022. So we really just took them from the SOK that we did beforehand. That's why we had this data set. Although these data sets are readily available now, right? So we have not specifically looked into whether the most recent attacks are somehow less detected or more detected. But I'm rather confident that, I mean, if the model data, right, if the model is being trained on sufficient data, then any new kind of transaction should be quite abnormal, right, in the way that it's built. For example, if you use self-destruct in a very fancy way, right, then I think, I guess, but we would need to quantify obviously through running the mechanism. I guess that the model would flag this as a less likely trace.
Thanks. Do we have further questions in the room? No, everybody. You.
Just maybe a comment. The reason people do the attacks on a live network to practice is to see whether you get front run, to see whether the flash bots pick it up, and that's kind of part of the attack, to see if someone takes the attack before you do.
Right, but you mean on a live network? You mean the sanity checks, or?
No, you just said you didn't understand why people tested their attacks on a live network before they run them. The reason they do it is because they're checking to see if flashbots front run them and take their attack. So they do a smaller version of it, and then they can see whether or not someone takes the money they were planning to steal.
Oh, I see what you mean. It's true. I mean, but that's quite dangerous, right? Like, why would you tell somebody your strategy, and see? Okay, because I would assume, right, if flashbots were front running an attack, then they also have the capabilities to optimize your parameters, and then they just need to take your strategy and optimize your parameters a little bit, and maybe it takes them a few seconds to then send out a more powerful version of your strategy. But yeah, I mean, these things are evolving. It's a cat and mouse game. I think this is a very good possibility indeed. I mean, the reason I'm kind of skeptical of why people are sending out test transactions is because everything can be simulated locally, right? There's no reason to, but I understand your kind of angle where you want to check whether other people are picking your thing up. Exactly. It's very good.
Thanks. Great exchange. So let's thank our speaker very much.